Hello everyone. Now I will continue my exercise. I'm assessing a conversion of a gas producer to CO2 injector. And of course, for CO2 storage, we want to maintain CO2 to be in a liquid or supercritical, or we also call it in a dense phase along the wellbore when the CO2 is injected. Okay, so I have a base case. By base case, I mean the base case for the injection rate, the injection temperature at the wellhead, and injection pressure at the wellhead. Now I just want to check whether the CO2 in that base condition is in liquid or supercritical form. Okay, and to check the phase in Prosper, especially in the gradient traverse, you can check from the gradient, okay, or the mixture density. Okay, in gradient, if the gradient is 0.17 or higher in psi per foot, then it means that it is in liquid form, because 0.17 and above is actually in the range of oil. So oil, the lightest oil, will have pressure gradient of more or less 0.17 psi per foot. But of course, if the gradient is 0.4 or above, then it is like water, as heavy as water. That if you assess from the gradient point of view, but you can also check the mixture density. So when we are talking about liquid or supercritical CO2, then we are targeting density around 400 kilogram per meter cube or higher than that. Okay, so maybe I can change the mixture density first. Okay, I want to change it to kilogram per meter cube so we can more easily distinguish either it is in gaseous form or liquid form. Okay, so I will go to the unit setting. Okay, so this is the unit system. I will go to the density. This one, I want to change from pound per cubic foot to kilogram per meter cube. Okay, click OK. Okay, then go to the gradient calculation, gradient traverse. Now you can see the mixture density, the unit is changed to kilogram per meter cube. And now we are looking at 800s and 700s, 500s, which indicate liquid CO2. Okay, now let's go to the base case first. I will delete everything and then click done, or I will erase, reset all, click done. Okay, so I only have one default case. So for the first node pressure or wellhead injection pressure, it is at 1274, 1274 psig. That's the base case for the injection pressure at the wellhead. Water gas ratio, if you want to use your well as a CO2 injector, then water gas ratio of 0 stock tank barrel per MMSCF is a must, because if you have water in your flow, then it is very easily will be corrosive. Okay, so you need to maintain what you inject is actually pure CO2, no water whatsoever. And total GOR, it is a default number because we don't have oil in this operation. It's the gas reservoir will be injecting our CO2 into. So there is no oil in our discussion. Okay, so yeah, this is just a default number to indicate that the oil is very, very small, if not non-existent. Okay, and inlet fluid temperature is 95 degrees Fahrenheit, and I'm targeting to 17 mmscf per day. And then, yeah, gas rate type, gas rate. Okay, first node, Christmas tree. Last node is at this depth, which is the depth of the perforation or the completion. And tubing correlation, yes, maybe I can use this correlation or maybe this one. And I read literatures, they say they use Bex and Brill. Okay, you can also use Bex and Brill. But yeah, if you check at the Prosper tutorial for a CO2 storage, CO2 injector, what they use is actually this one, if I'm not mistaken. Okay, so for this table, I have the MD, measured depth, true vertical depth, TVD, the pressure, temperature. Okay, that's good. Gradient and mixture. Okay, good. So let's check. Just click calculate, show calculating data. All right, what happened here? So you see here, if you inject at this condition at inlet fluid temperature of 95, then at this section, okay, it's like gassy flow, okay? But if you check at the mixture density, it's quite heavy, okay? The CO2 or the CO2 in this section is actually more or less a liquid form, but we are not that certain because here we have very small mixture density, okay? And also in this section, okay? Yeah, it is very difficult to know the detail because at the end of the day, if you want to know all the reasons of how the pressure and temperature will look like this, then you need to break down the correlation, okay? Then you need to break down this tubing correlation that I use petroleum experts. By the way, if you change to Bex and Brill, what happened? Calculate. It's quite weird also, right? Here we have this section, the density is very small. Okay, yeah, that's big. Maybe in part because I'm injected the CO2 at the very high injection rate, 17 mmscf per day. So there will be pressure losses along the wellbore. As you can see, the gradient is negative. But I can say that this is not a very good or promising condition. I want to be sure that the CO2 will be in the liquid form or supercritical form. Then this trend, this profile is not so reassuring. Okay, so what I'm going to do, yeah, I will do some scenarios. I want to check at what maximum temperature at which we can maintain dense phase CO2, or what is the minimum injection pressure at wellhead to achieve dense phase CO2, or what is the maximum rate to maintain or to achieve the dense phase CO2. Okay, so that's the scenarios, the exercise that I'm going to do. Okay, but of course I need to record this message, this observation first. So go back to this correlation then. So I can say that in this condition, in the given wellhead injection pressure, in the targeted gas rate, and in the given fluid temperature, 95 degrees Fahrenheit, I cannot I cannot maintain, I cannot be sure, okay, that I can achieve dense phase CO2 along my wellbore when I'm injecting my CO2. Okay, so I will take a picture of it, and Yeah, maybe I just will save this case and then I will copy the file and then I will create, I will copy and paste and create another case where I will exercise. I'm looking for the minimum injection pressure. That's another case, and the other case is the maximum injection temperature and then the maximum gas rate, okay, to be injected. Okay, so this is the base case. Then I will run in total 4 cases. Okay, this is the base case. Then the second one is I will try to do temperature sensitivity and then rate sensitivity and then pressure sensitivity. Okay, so now this is the copy file. Okay, the copy file. As you can see, the header, gradient traverse, data entry, the name of the well, and then you see the temperature sensitivity. Now in this part, I just want to maintain the injection pressure. I want to maintain this one, the gas rate, and then I will vary the temperature. I want to find the maximum injection rate at the maximum injection temperature that I can maintain to achieve liquid CO2 or dense phase CO2. So it's quite clear that you see temperature of 95 degrees Fahrenheit, maybe it's too hot, it's too high. Okay, CO2 will be in the gaseous form when I inject at this condition. So I will try to lower it down, 90 for example. Yeah, unfortunately, if you do cases like this, you open the drop-down menu, you cannot find temperature. So you cannot do exercise like when you do sensitivity with other parameters. Here, for the temperature, you need to do manually, like the one I'm showing you right now. I change it to 90 degrees injection temperature and then calculate. And then, yeah, it's not very promising. From the mixture density, actually, it's quite high, but actually the temperature is decreasing. So friction pressure is higher than hydrostatic pressure. So that's why the pressure is increasing. I don't think that's very safe. So yeah, what I want to find is actually where the pressure is increasing as we go down deeper and deeper into the bottom hole. Okay, so again, injection temperature of 90 degrees, maybe it's still too high. So let's lower it further, 85 degrees. Hmm, it seems better, but of course, from the gradient, you see the gradient, it's a gas gradient. Okay, it's a gaseous gradient. Yeah, maybe it's not a gas gradient, but so looking at the gradient is, it's just one indicator because at the end of the day, the gradient is not showing only hydrostatic pressure, but also friction pressure. So something like that. But actually here, the most important thing is the mixture density showing 700, which is actually already dense phase CO2. So what if we go back to 95? Let me try to think first. So here the temperature is 500 psig at temperature of, oh, but the temperature is already quite low. So at that pressure, yeah, it's actually liquid form, but I'm not I'm not so sure about this mixture density. So can I change it back? I'm not so sure that at this pressure and then at this temperature the density is 800. Okay. So if you, for example, go to the phase diagram. So I click done and then go to this one and then I will generate the phase envelope and then plot here at pressure of 500 and then at temperature of, yeah, actually we are at liquid form, but unfortunately I cannot draw density in this plot. Do I have density in this plot? Click. If I close view profile, I don't know. I don't have density, unfortunately. Hmm. Let me try. Do I have density? Not so sure. Plot, redraw. There is cannot display. Unfortunately, it's better if we have density here. So okay, gradient reverse again. Yes, it's quite, but yeah, a problem here and here. But I'm still not sure about that the density will be that high. 800 kilogram per meter cube. It's just too high, and at this pressure, this temperature, I'm not so sure. And can we, if we check the layout, can I plot liquid density, for example? Click done. So liquid density and mixture density will be the same. Let's say gas density, just want to check, done. I don't have the gas density. Where's the gas density? Oh, here. Yeah, oh, you see gas density here, 0.001 kilogram per meter cube. Oh, so yeah, this is the thing that I still don't understand. The gradient or the regime? Do we have the regime here? No. Click layout. The regime here. Regime. Guess, right? All right. So yeah, let's see if I just cool down to 0. I want to check the regime. So now it's bubble. It's bubble. Okay, so bubble, then it's one indicator that, yeah, if you have bubble flow regime, then of course the dominant phase is liquid, where the gas phase will be dispersed as bubbles. So having bubble as your regime, it is one indication that you are working at liquid CO2 or supercritical CO2. Okay, and if you go to 95, you have gas flow regime, then of course it's not it's not good. So that's why you have -8 e to the power of -8 here. That's one indicator that you are not working in the CO2 phase during this base condition. Okay, so I'm just gonna uncheck this one. Okay, and then let's maintain the regime, and let's check also the hold up. Okay, hold up. Hold up of 0. It's actually liquid hold up. So hold up of 0 means everything in gas. Okay, so let's maintain hold up in regime then. And then I'm just going to, yeah, something like this. So 95 out of question. Now let's just lower down the temperature. Okay. Hold up 0, still gas. 85. Yeah, something that makes this well is quite difficult is that the reservoir pressure is too low. It is 330. Okay, so yeah. So that's one factor that makes maintaining the liquid phase is more difficult. Okay. All right, so it's gaseous here. Cannot 80 degrees Fahrenheit. Okay, it's not that good. All right, and you need to lower it farther down. 75. Still cannot. Okay, and then 70. It's already quite cool. Still, you have gas there. So yeah, let me check at my picture. If you inject at pressure of that high and the temperature is 90, actually at 90, if I check, and then it's already liquid. So why this regime is gas? Yeah, something like this discrepancy in the tool. Bex and Brill says, okay, this one is some discrepancy there. So let's make it 68 room temperature. It's all liquid. I just want to change it to petroleum expert 2. Calculate. All right. It's difficult. It's just because this regime, but based on the density, it's already good. Let me think. 80. Okay, so close to 100 degrees. The okay, so if you go back to this one, base envelope here. So if you okay, let's see. So this is the critical temperature. So here you have supercritical. Here you have liquid and supercritical. So actually we are working at quite high, and then if you have temperature quite high, then here, yeah, let's see if here, right? Let's see, for example, exit. Okay, go back to the gradient. Here, just check it. 1568 at temperature of 99 or practically 100 degrees Fahrenheit. Go to here, phase envelope, plot 100 degrees. Okay, 100. And then go to pressure of 1500. Oh, so legend box y-axis number 2, but unfortunately I don't have density. I don't have density. Yeah, let's say 2000. Yeah, somewhere here it's actually super critical. So if we go back to the base case itself, and then I calculate, this is the question, 582 at practically 50 degrees Fahrenheit. So, or I can capture this one and then go back, face envelope, plot. Okay. 500 first 50 degrees Fahrenheit. 50 somewhere here, and then go up 500 what, 582, 50 degrees. You can see XY here. X is temperature. I just want to find 50, yeah, here, and then 582. Oh, this one is in gas phase. So at best case, I cannot achieve liquid CO2 at the bottom. I will lower down, done, and then go to calculation 90. Okay, and then I'm just going to keep this one. Okay, or all of the, okay, click done, and then go here. Yeah, this is the exercise that you do for temperature, because we cannot run many cases with temperature. We need to find it manually, like the one I'm doing right now. Plot. Okay, so at the bottom hole, my temperature is 93, somewhere here, and then pressure 1170. So I go here, 93, somewhere here. What pressure? The pressure 1170, 1170, 93. Somewhere here, it's super critical. Super critical. So yeah, I just want to check here at the middle. 92 at 1261. 1261. 1261 here. 1261 at 92. Yeah, supercritical. So I think my conclusion for injection temperature of 90 degrees is it's safe. It's in liquid form actually. Okay, so I'm just gonna neglect the regime. Okay, I will uncheck the regime then to avoid misinterpretation. Okay, so here although the gradient shows very small, yeah, it's because you will still suffer friction pressure that is quite high, so it will cut the gradient. Okay, although you have high hydrostatic gradient due to liquid phase, but the friction pressure decrease the final gradient. But based on density, mixture density, the phase is quite heavy. It's quite heavy. So that's why we can say that. And if you check the phase diagram, it's safe. Okay, so maybe I just gonna take a picture of it. Okay. Curve detail. Yeah, unfortunately, I cannot plot density here. It's just gonna be better, I think. Select curve, show all. Cannot. I only have pressure and temperature options. No output. No scale. No legend. No period. Okay. Okay, then I just gonna take a picture of it. And the lower the temperature is, the more sustainable the CO2 in the dense phase will be. Okay, so yeah, I think we can stop here because this is the temperature sensitivity to find the minimum condition that is required, that is needed to achieve CO2 dense phase CO2. And yeah, I varied the injection temperature. I started with 95 degrees Fahrenheit at wellhead, and it shows gaseous phase. So like this, gaseous phase based on the density here and here. Okay, I'm not quite sure about this, so I just lower down. Actually, I should do lower down with only 1 degrees Fahrenheit, like 94. And then what will happen, right? Okay, still a problem at this section. Okay, and then 93, what will happen? But of course, it is quite time consuming. So I'm just gonna go directly to 90, psychological number, of course. And as you can see, everything good, everything good. So yeah, we can take this result. Okay, so I think I can stop here. Thank you. So I hope what I've just presented to you, you will understand it better, how we exercise and how we find the base condition to achieve dense phase CO2 when we want to inject CO2 into our storage, our reservoir. That will be the storage. Okay, that's all. See you soon. Thank you.